Welcome to the course on risk modeling in insurance. This video discusses the use of mixing and splicing to construct more flexible loss distributions from given basic loss distributions. Now, to construct more flexible distributions, starting from those given loss distribution functions, the techniques of mixing and splicing are useful. Both constructions assume that two or more separate processes are responsible for generating the losses. However, with a mixture construction, we assume that various processes operate on subsets of the population. For example, in a dental claim setting, one process may generate losses of a fixed amount corresponding to some specific interventions by the dentist, whereas other losses are more variable and will be represented with a different process and thus a different distribution. Typical for a spliced distribution is that different loss models will govern losses from different intervals. For instance, you will use a distribution for small to moderate losses together with a distribution for large to extreme losses. You will first consider an example of continuous mixing in the context of modeling insurance losses. Similar to the construction you derived for count data, let X follow a conditional probability density function with parameter lambda. Instead of fixing a value for lambda, you will now assume that lambda is a realization of a random variable, capital lambda, with a certain density. The unconditional PDF of X then follows from the law of total probability, as is demonstrated here on the sheet. Now here is an example that illustrates the construction of such a continuous mixture. Suppose lambda has a gamma distribution, and given lambda equals lambda, X has an exponential distribution with parameter lambda. The question is then, what is the unconditional distribution of X? Well, you will solve this exercise by writing down the expression for the probability density function of X as the integral over all values of lambda of the conditional density of X given lambda multiplied with lambda's marginal density. Do note that lambda, in this example, only takes positive values, and therefore the integral's domain runs from 0 to plus infinity. Now you plug in the exponential density for the conditional density of X given lambda and the gamma marginal density for the density of lambda. You will rearrange the expression to conclude that the resulting mixture distribution is a Pareto distribution, or Pareto density. It is insightful to note that the resulting distribution, the Pareto in this case, has a more heavy tail than the distribution you started from, the exponential. This makes the Pareto more suitable for modeling losses that are large or even extreme. Now, next to the continuous mixture we just discussed, you may also consider discrete mixtures of basic loss distributions. In this example, you consider a mixture of Erlangs distributions. The mixture, as proposed here, is a so-called variable component mixture, where M is a random variable and refers to the number of components in the mixture. The weights alpha are positive and they sum up to 1. The Erlangs distributions used in the construction over here are specified with positive integer shape parameters Rj and a common shape parameter theta. So altogether, we have a variable component mixture with capital M number of components in the mixture, weights specified by the alpha j's, and the densities that we use are the Erlangs densities. Note that the density of the Erlangs distribution is in fact the density of a gamma distribution where the shape parameter Rj has to be a positive integer. Here you see a couple of shapes of possible Erlangs distributions with varying shape in this case and with varying scale parameter in this graph. Now, these mixtures of Erlangs are suitable for modeling insurance losses because they offer a versatile class of distributions, in the sense that mixtures of Erlangs are dense in the space of positive continuous distributions. This implies that any positive continuous distribution can be approximated up to any precision with a mixture of Erlangs. They are mathematically tractable and they allow analytical expressions of quantities of interest, for instance, the stop-loss moments, the value at risk, the tail value at risk, and so on. They have a fitting procedure available that is based on the expectation maximization algorithm, the EM algorithm, which allows to accommodate for censoring and truncation. And this fitting procedure is directly available. You can implement it easily in a software like R. Now, more on the use of those mixtures of Erlangs for risk modeling is covered in the following series of papers. So the first paper focuses on the calibration of univariate mixtures of Erlangs. The second paper here covers multivariate mixtures of Erlangs. And the last paper combines the light-tailed mixtures of Erlangs and the light-tailed Erlang distribution with a heavy-tailed extreme value distribution in order to achieve a global fit procedure. So you're invited to have a look at those papers, and you can have a look at the implementation of the EM algorithm by following the link over here. So this is a bit of background on research on loss models with mixtures of Erlangs. Now, to conclude the discussion of mixtures of Erlangs, you see here the fit of such a mixture on a dataset with reinsurance losses from Belgium. Losses are registered above 1.2 million euro, and the resulting mixture uses two components with weights 97% versus 3%, and the shape and scale parameters as listed over here. So those are calibrated using this EM strategy, and you see here the results of this calibration procedure. Essentially, one component in the mixture, the one that gets weight of 97%, captures the body of the losses, and the other component in the mixture captures the tail of the losses. The resulting mixture gives a good fit as illustrated by the density histogram, that's top right, the survival function, that's bottom left, and the QQ plot, that's bottom right. In each of these plots, we compare the empirical data against the fitted distribution, and we conclude that this gives a good fit for the given dataset. Next to mixing distributions, the technique of splicing offers a valid and useful strategy to construct a new, more flexible loss distribution out of a set of given basic loss distributions. And with splicing, you will start from K probability density functions, denoted here with F1 up to Fk. And here we assume, having positive losses in mind, that they have their support on the positive real line. A new probability density function is then constructed by splicing, and that goes in the following way. For a loss x between 0 and C1, the density is specified as P1 times F1 star. For a loss between C1 and C2, the density is P2 times F2 star, and so on and so forth. Well, those P's, P1 up to Pk, they act in this construction as weights. So they must be positive and sum up to 1. On the other hand, the Fi stars, those denote legitimate probability functions having their support on the interval between Ci-1 and Ci. So that means that Fi star is defined only on the interval and is 0 outside of this interval. And moreover, all its probability mass should be put into this, should be spread in this interval. So how do we get those Fi star densities? Well, the Fi star, as said, is a legitimate PDF based on a given probability density function Fi, where Fi originally had the positive real line as its support, and we obtain Fi star by restricting the density Fi to the interval Ci minus 1 Ci. So how do you do that? You're going to work with conditioning, and you're going to use the construction as is specified over here. So eventually you get a density that is defined on the interval between Ci minus 1 and Ci, and that takes a value 0 outside of this interval. It is important to be aware that splicing does not ensure that the resulting density function is continuous. That is, it is not sure, or it is not guaranteed a priori, that components will meet at the breakpoints. And the breakpoints are those points C1, C2, and so on, where we glue the two components together. So to conclude this video, you will see a detailed example here of a two-component spliced distribution. The example combines an exponential distribution for losses in the interval from 0 to C with a Pareto distribution for losses in the interval from C to infinity. Now, intuitively, the exponential model captures the body of the loss distribution, and the Pareto distribution captures its tail. So your starting point are the PDF and the CDF of the exponential on the one hand, as shown here, and the PDF and CDF of the Pareto distribution on the other hand. The spliced probability density function then follows by restricting the exponential to the interval from 0 to C through conditioning, and by restricting the Pareto to the interval from C to infinity, again by using conditional probabilities. The weights in this construction are denoted here with P1 and P2. They must be positive and add up to 1. Filling in all the formulas from the previous sheet, you can verify the expression as shown here on the sheet. Now, in this particular example, the resulting PDF printed on top of the sheet is not continuous in the breakpoint. That's the point C in this example. So you see here at the bottom of the sheet a particular example of this splice distribution with an exponential for the body of the losses and a Pareto for the tail of the losses. This example is obtained by plugging in certain values for C, for the weight, for lambda, for the parameter alpha and beta in the Pareto distribution. And you indeed see here that the resulting PDF is not continuous in point C that equals 100 over here. So this concludes the video on constructing flexible loss distributions through mixing and splicing.